All right, here we are. We're at Chapter 7, problem set number 1. Problem says, in the figure, there's graphs. They give the x component of the fx of the force acting on a particle moving along the x-axis. Rank them according to the work done by the force on the particle from x equals 0 to x equals x1, from most positive work first to most negative work last. All right, so we're trying to find the work done. Nice and easy one to start with. The thing we know is that the work done is equal to the area of the f versus x graph. Now, this is the area, colloquially we say area under, but what we really mean by that is the area between your graph line and the axis. So if we look at this first one here, let's shade the area. So that's that area. Let's do this one. I can already see there's a lot more negative area here. This one. And this one. So what I'm noticing right away is we're looking for the positive area and the negative area here. We'll notice that the area, like this one here, this area is positive and this area here is negative. Same thing at this one here. This little area is positive, this one is negative. This one's positive and this one's negative, and this is negative and this is positive. So it says rank them from most positive work to most negative work. Okay, so let's do that. So we have most positive, and here most negative. Well, I'm noticing this one is clearly, so I would say that this is the most positive. This is interesting because this one over here, this looks like it's 0, so go A, and then looks like C, and then P. So the work is the area, and I shade the area, and there we go. So this one's about a pig who's going to attempt to slide down here. So I didn't draw the pig, but we'll make a little stick figure dude instead. Here's a little stick figure dude, and he's going to slide down. Okay, we have our A, B, and C here. And the question is specific. It says, rank the slides according to how much work the gravitational force does on the pig during the descent. All right, so again, our definition of work is equal to the F times the D that are parallel. Now, this can you can either adjust this so that the force is parallel to the distance or the distance is parallel to the force. And in this one, I actually think that if you were to look at any moment, let's say on this one, for example, we know the gravitational force is down. Okay, the gravitational force is straight down. So that's one of our vectors. And then the distance that it's going here, right, it's sliding along this way. So this is our distance vector for this one here. So I think the easiest thing to do is to notice that all three of these are going to have the same force vector. And so if they all have the same force vector, how do we kind of figure out what's going on here? Another way to, well, let's do the force vector first. So even though the force vectors are the same, when you break them up into their component parts, we can see that this part here is the mg sine theta. Each of these is going to have a slightly different mg sine theta, so it's a little harder to figure this out. For example, if I look at this one, this mg sine theta is going to be much different than this one. You can see the steeper the ramp, so I think this is a little more challenging because you're noticing that as you go from ramp to ramp to ramp, the mg sine theta is getting smaller, but the distance is getting bigger. So I don't think that's the easiest way to conceptualize this. So let's, instead of trying to make the mg sine theta parallel to the distance, let's think about just the mg and see if we can make the distance somehow the same. So we know that the work done by the gravitational field or the gravitational force is going to be equal to the gravitational force times the distance that's parallel to that. Well, our gravitational force is mg, and this is in the down direction, so we need the distance that's in the down direction. And if you notice, all of these are falling for the same height. So this mgh is true for all of them, so because they have the same mg and they have the same h, the h is the distance that's parallel to the height, I would say that these are all same work done by the gravitational force. So I think that's the easiest way to conceptualize this one, is to take the, instead of trying to figure out how I'm going to make the force parallel to the distance, why don't I take the distance that's parallel to the force? I think that's easier. Okay, problem 5. It's a little dicey. So it has a father and son that are racing. So it starts out, it says, a father is racing his son, has half the kinetic energy of the son. So I'm going to write that in a notation, hopefully that makes sense. So this says the kinetic energy of the father, Kf, is equal to 1/2 the kinetic energy of the son. So let's start with that as our first understanding here. And it says the son has half the mass of the father. So let's write that over here. So the mass of the son is equal to 1/2 the mass of the father. Right? That sounds pretty good to me. Then it says, the father speeds up by 1 meter per second, then he has the same kinetic energy as the son. What are the original speeds of the father and son? So let's write that. So I'm going to say there's a new kinetic energy of the father. And one way we write that is we write kinetic energy of the father. And I'm going to use this little, it's like an apostrophe. We call it prime. It just means like one that's different than this. So even though I'm using the same variable. It says 1/2 the mass of the father times the original speed of the father plus 1 all squared. Now, what this says is it says this is equal to this original K-son over here. So I'm looking at this, I know this is a K-father, this is a K-father because it has this, and so I wonder if I can set this one and this one equal to each other somehow. So if I multiply both sides here by 2, I end up with 2 times the kinetic energy of the father is equal to the kinetic energy of the son. I just multiply both by 2. And I look over here, and this expression is also equal to the kinetic energy of the sun. So this is equal to that right there. So now I have these two things, and I wonder if I can kind of express them and then work it out. So let's try. So how do you express kinetic energy? So 2 times 1/2 mass of the father squared is equal to, I'm going to get rid of this, let's do this one. And now what I like about this is I can have some stuff kind of magically disappear. I can expand this out. So this is 2 times a half, so this goes away. So I'm left with, I'm going to switch colors because it's one statement now. So this is one new statement. So these disappear, and the mass of the father disappears. So I end up with v father squared is equal to 1/2. I'm going to expand this. So because it's squared, I just expanded it there. Multiply this by 2. And if I expand this, I end up with v father squared plus 2 v father plus 1. I'm going to have to factor here. So I can either move this over here, I can move all this over here. It doesn't, the algebra itself doesn't matter. If I subtract this from both sides, I end up with v father squared minus 2v father minus 1. And I'm going to put this into my handy dandy calculator, and I end up with the speed of the father is equal to 2.4 meters per second. So I feel pretty good about that. And now what I'm going to have to do is I'm going to have to come back up here, and I'm going to have to look at one of these here, because I still need the speed of the sun, right? I still need the speed of the sun. So how are we going to get that? I can look at this original statement here. I'm going to do it in orange. Bring this one over here. So what I have is the kinetic energy of the father, which is 1/2 mass of the father, v father squared, is equal to 1/2 the kinetic energy of the sun, which is 1/2 mass of the sun, v sun squared. Okay, so this is an algebra problem now. We're going to need this piece of information right here, that the mass of the sun is 1/2 the mass of the father. Okay, so I can plug that in on either side. Because it says mass of the sun, I'm going to plug that in here. So so 1/2 of a half is a fourth. Now I'm going to make the substitution here. Mass of the sun is 1/2 the mass of the father. Okay. So I go to simplify here. I have a half on both sides. I can multiply both sides by 2 and make those disappear. I can divide both sides by mass of the father, make those disappear. And I end up with that the v father squared is equal to 1/4 v sun squared. If I square root both sides, the speed of the father is equal to 1/2 the speed of the sun. So that means the speed of the sun is equal to 2 times the speed of the father, which is 2 times 2.4, so it's 4.8 meters per second. All right, problem 13. So problem 13 talks about a luge rider. So I don't know if you know what a luge is, but it's an ice sled that they use. And what happens is they go down a mountain through some turns, some twists and turns, and then they come out and they have to brake, basically is what we're saying. And so if I say the luge looks something like this, right? It does not look like this. This is just what I'm saying it looks like. Okay, and there could be a guy on it. There. And he's coming in hot. He's coming in hot. So it says a luge and its rider with a total mass of 85 kilograms. So let's write that down. Total mass of 85 kilograms. Emerge from a downhill track on a horizontal straight track with an initial speed of 37 meters per second. If a force slows them to a stop at a constant rate of 2 meters per second per second. All right, so two things are in there. It says the final speed is equal to 0 meters per second, and it says the acceleration is, now it says 2 meters per second, but it's slowing them, and their velocity is positive, so we're going to make that one negative. So it says, what magnitude of force is required? What is the distance they travel while slowing? And what work is done on them by the force? So there's actually a couple different ways to do this problem. I think the way that they want us to do it you could do a force times distance, you could do a change in kinetic energy, or you could do it using the kinematic formulas. All these are good ways to do this problem. So let's look at it. First question is, what is the force? So let's draw a quick force diagram and see what that looks like. So here's the weight. Here's the normal force, and there has to be some stopping force here. Ostensibly it's some kind of friction, but it's a stopping force. And what we notice is that this is the net force. This is what we're looking for. And that's equal to the mass times the acceleration. The mass is 85 kilograms. The acceleration is 2. So the stopping force has to be 170 newtons. Now, it's negative because it's pointing left, and that's in there, so I'm okay with that. So that's the force. What distance do they travel while slowing? So I'm going to show you one way to do it with the kinematics, because I think the kinematics are instructive in terms of what we already know. So we know that we have delta x, v0, v final, a, and t. So this is what we're looking for. We're going to call this d. The initial velocity is 37. The final velocity is 0. The acceleration is -2. I know that v squared is equal to v0 squared plus 2a delta x. 0 is equal to 37 squared plus 2 times -2 times d. So I'm going to solve for d. D is equal to So d is equal to, and we'll round a little bit, 342 meters. So that's one way to get this, easy way. What work is done on them by the force? All right, so let's find out the work. One thing we know is that work is equal to the force times the distance. I figured out my force was 170. The distance is 342. So the work done is about 58,000. I got 58,140. Energy and worker in joules. Now the textbook is going to round a little bit for significant digits, but if you're getting 58,000, you're probably doing it right. Now, the next question here is, what are the force, distance, and work if they slow with a different acceleration completely? So what we're going to do here is we're going to change our acceleration. We're going to change our acceleration to -4 meters per second. And we're going to see how things change. One thing you'll notice here is that now if I go to calculate the net force, we can see that the force is much greater because it's going to be 85 times the 4. And so 85 times 4 is going to be twice that. So how about 340 newtons? So twice the force. And the next thing it wants to know is what is the distance, the slide distance. Okay. Well, looking back at this equation here, if v squared is equal to v0 squared plus 2a delta x, 0 is equal to 37 squared plus 2 times -4 times the new d. Right? What's happening here is I'm going to take my 37 and basically I'm dividing it by twice as much. So the new distance is going to be 171. Now we can see that that's going to be half that, which is fine for us. That makes some sense. But here's the thing that's really cool, is that when I go to calculate the new work here, I'm going to take the force times the distance, and I'm noticing that the force is 340. It's twice what it was, but the distance is 171. It's half, and so I end up with saying, we actually could have intuited this in a different way, just based on the fact that if the work is equal to the change in the kinetic energy, what that means is that the cart went from 37 to 0. The kinetic energy was the same, the change in kinetic energy was the same on this side as it was on this side. So since the change in kinetic energy was the same, I would say that the work done is also the same. All right, let's go on to number 15. 15 gives this figure here. So it says 3 forces applied to a trunk that moves leftward 3 meters over a frictionless floor. The forces are 5 newtons, 9 newtons, and 3 newtons. My arrows are not drawn to scale. And the angle between F3 and the horizontal is 60 degrees. During this displacement, what is the net work done by the 3 forces, and does the kinetic energy of the trunk increase or decrease? Now, there are 2 ways to do this. One way to do this, if you wanted to find the net work done. So this is the net amount of work. You could take the net force and multiply by the distance that's parallel to that net force. So in this case, that would be the horizontal direction. You can totally do that, and that's one way to do it. The other way to get the net force that I think is a little bit more instructive here is you can get the network. To get the network, you take the work done by force 1, add it to the work done by force 2, add it to the work done by force 3. This is going to be slightly more instructive in this context. We're going to do it this way. So let's do work 1. Well, force 1 is this way. So I need F times D that are parallel. This is easy because this force is 5 newtons, the distance is 3, and this force and this distance are already parallel, so this is 15. the work done by force 2 would be equal to FD that are parallel. But the thing about this is that this force is up and to the right, so we got to figure out what's the right direction here. So we have the two components here. That's the F in the X direction. So this is the F in the Y direction. This one here is the F in the X direction. And we see that the F in the Y direction is perpendicular to, not parallel to, this distance vector here. So the only one that works here is this Fx. So I'm going to take my F in the X direction and multiply by this distance. But here's the thing. You'll notice that this is to the right and this one is to the left, which means we then have to multiply by -1. If we were using the cosine formula for this instead, this would be the cosine of 180 is -1, so that's where that -1 comes from. The F in the X direction, if this is 9 and this is 60 degrees, this is 4.5. And the distance is 3, and we need our -1. This is -13.5. And let's do the work done by 3. So I need F times D that are parallel. Well, here's the thing. This force is straight down. It has a value of 3. But what distance does it move that's parallel to this? And the answer is 0. It does not move at all in that direction. And so there has to be some component that's in the same direction. And if not, it's 0, because this is 90 degrees. So, given this context, let's go back and express our network. This is positive 15, this is minus 13.5, this is 0, so my network is 1.5, and its energy, so it's joules. The second question says, does it increase or decrease? Does the kinetic energy increase or decrease? And the answer is it increases. Some people said it increases because our thing is speeding up in this direction. You don't actually know that or not. Like it could already have been moving and be slowing down. We don't really know. We know the kinetic energy increases because the work is positive. And since the work value is positive, our kinetic energy is increasing. All right, that brings us to the end of Chapter 7, Problem Set 1.